Look closely at the physical laws governing reality. The math that dictates the standard model of particle physics and general relativity operates with a precision that has been confirmed to 13 decimal places. Governing this machinery are 25 parameters. They are arbitrary numbers plugged into equations to fit observed data. Shift them infinitesimally, and the entire structure fails. Alter a down quark's mass or electromagnetism by a fraction of a percent, and stars fail to ignite. Chemistry collapses. In the 1970s, physicists offered a philosophical solution to this exactness, called the anthropic principle. It suggests that the universe has these exact parameters simply because if it didn't, we wouldn't be here to observe them. We exist, so the parameters must logically permit our existence. This chart visualizes a mathematical critique of that idea by biologist Stuart Kauffman. Our universe naturally produces 98 stable atoms. Yet biological life and the rocky planets required to host it only require a small subset of 19 specific light atoms. If our cosmic parameters were dictated purely by the requirements of biology, the existence of those other 79 stable atoms makes no mathematical sense. A philosophical observation falls short. Physics requires a concrete cosmological mechanism that actually generates varying laws of nature. The search for that mechanism starts fractions of a second after the Big Bang, during an epoch called cosmic inflation. The early universe underwent a brief, violent period of exponential space expansion, stretching microscopic fluctuations to macroscopic scales. This diagram outlines the mechanics of eternal inflation. It shows that expansion doesn't end everywhere simultaneously. Driven by quantum fluctuations in the false vacuum, the surrounding space continues to inflate endlessly, leaving behind stable pocket universes. At the same time, string theory calculates that the extra dimensions of spacetime can be folded in roughly 10 to the power of 500 different ways. This vast collection of possibilities is known as the landscape. When these two concepts merge, a physical mechanism emerges. Every time a new bubble universe nucleates in the inflating background, it randomizes its extra dimensions, adopting one of those 10 to the 500 configurations. Each new bubble inherits completely different physical laws. Quantum mechanics offers a separate, mathematically deterministic route to parallel realities. Formulated in the 1950s by Hugh Everett, the many worlds interpretation argues that wave functions never collapse. Instead, every possible outcome of a quantum measurement is physically realized in a branching, divergent reality. Whether through eternal inflation or quantum branching, the result is a level 2 multiverse. The specific tuning of our 25 constants is explained by probability. We inhabit the specific pocket universe where the cosmic lottery generated the exact numbers required for biological survival. Not all physicists accept a spatial multiverse. Theoretical physicist Roger Penrose proposed a competing mathematical model called conformal cyclic cosmology. This model discards inflation entirely. Instead, there is only a single universe, iterating through an infinite sequence of temporal cycles. Penrose calls each individual cycle an eon. The mechanics of an eon depend on its distant future. As a universe expands endlessly, all massive particles, like protons and electrons, eventually decay. Ultimately, the cosmos is populated entirely by massless photons. Without mass, distance and proper time cease to have any physical meaning. The universe dissolves into a state where mathematical scale is entirely irrelevant. Because scale is removed from the equations, the infinitely large, freezing future of an old universe can be smoothly, conformally attached to the infinitely hot, microscopic singularity of a new Big Bang. This theory approaches the fine-tuning problem from a temporal direction. We aren't a lucky bubble in an infinite spatial lottery. We are experiencing one specific, perfectly tuned eon in a never-ending sequence of cosmic rebirths. For decades, both the spatial multiverse and conformal cyclical cosmology were treated as untestable mathematics. Today, astrophysicists know both frameworks make highly specific predictions that can be detected. This is the cosmic microwave background, the primordial afterglow of creation. Its temperature fluctuations serve as a raw dataset, a cosmic canvas where interactions from outside our observable universe would leave physical scars. If eternal inflation is correct, our expanding universe should have collided with a neighboring pocket universe in the distant past. A collision would send a cosmic wake rippling through spacetime. On the map, it would manifest as a highly symmetric, disk-like temperature perturbation, characterized by a specific geometric pattern known as E-mode polarization. Conversely, if the universe is cyclical, the data should reveal circular anomalies known as Hawking spots. These spots would appear as concentrated rings of energy. They are predicted to be the final radiation bursts from the evaporation of supermassive black holes that existed in the previous eon, bleeding through the conformal boundary into our own. To hunt for these scars, cosmologists have analyzed data from orbital observatories like the WMAP satellite. As of right now, the data does not definitively confirm either the cosmic wakes of a multiverse or the Hawking spots of a previous eon. The current temperature maps place strict limits on eternal inflation, calculating that the probability of detectable bubble collisions on our sky is constrained to fewer than 1.6 occurrences. Even without immediate observational proof, the threshold has been crossed. Physicists have defined the mathematical boundaries of parallel realities and cosmic eternity. We are actively analyzing the scars of creation to map our exact place within infinity.